Hi everyone, my name is Ishay and I would like to tell you about the complexity of finding fair independent sets in cycles. Our story starts in 1986 when Dusu and Wang have studied the cycle plus triangles problem. In this problem, we are given a graph G on 3 times n vertices, whose set of edges is the disjoint union of a Hamilton cycle and n vertex disjoint triangles. Consider, for example, the cycle on 15 vertices in the figure, and suppose that the 3 yellow vertices form a triangle in the graph, and that the red vertices form another triangle in the graph, and so on. Every color corresponds to a triangle in our graph. Dusu and Wang asked whether such a graph must contain an independent set of size n. Or equivalently, if one can choose one vertex from each triangle to obtain a set of n vertices with no two consecutive vertices along the cycle. They conjecture that the answer is positive, and as you can see in the figure, the 5 highlighted vertices form an independent set in the cycle, and it includes one vertex from every color. When Erdős heard about this question, he proposed a stronger conjecture, saying that such a graph is in fact three-colorable, meaning that the vertex set can be partitioned into 3 independent sets of size n. Looking again at our example, you can see that the graph has another independent set of size 5, and there is another one, so this graph is indeed three-colorable. Both the conjectures of Dusu and Wang and of Erdős were confirmed by Fleischner and Stibitz in 1992. In fact, they proved the conjecture in a stronger form with respect to the least coloring variant of the problem. Their proof used an algebraic approach of Alon and Tarsi based on polynomials, and an alternative proof for the three-colorability result was then given by Sachs. These proofs, however, are not constructive in the sense that they do not supply an efficient algorithm with polynomial running time that, given a graph on 3n vertices whose set of edges is the disjoint union of a Hamilton cycle and n vertex disjoint triangles, finds a three-coloring of the graph, or at least an independent set of size n. Questions about the computational aspects of the cycle plus triangles problem were asked by several researchers over the years, but no hardness result is currently known for the problem. A natural generalization of the cycle plus triangles problem is that of fair independent sets in cycles. Let G be a cycle graph, and let V1 up to Vm be a partition of its vertex set into m sets. As example, consider this cycle, and let the yellow vertices be the vertices of the first part of V1, let the red vertices be the ones of V2, and so on. We are interested in an independent set of the cycle that includes roughly half of the vertices of every part Vi of the given partition. More precisely, we say that an independent set S of the cycle G fairly represents the partition if for every I from 1 to m, the number of vertices of S that belong to Vi is at least half the size of Vi minus 1. Notice that if each of the sets V1 up to Vm is of size 3, then the question here is closely related to the cycle plus triangles problem. In the graph from the figure, you can see that the highlighted vertices form an independent set that fairly represents the partition. For example, we have here 5 red vertices, and our independent set includes 2 of them, just as required. In a work of Aharoni, Alon, Berger, Chudnovsky, Kotlar, Lebel, and Ziv, it was shown that for every cycle and for every partition of its vertex set, there exists an independent set that fairly represents the partition. In a later work of Ishay and Munir, it was shown that if the number of vertices and the number m of parts of the partition have the same parity, then not only that there exists an independent set that fairly represents the partition, but there are even 2 disjoint such independent sets that together cover all the vertices of the cycle, but one from each part Vi. So let's highlight in the figure another independent set that fairly represents the partition, and notice that together with the previous one, they miss only one vertex from each color. It's interesting to mention that although the statements of these results are purely combinatorial, their proofs are based on tools from topology. The first application of topology in combinatorics was obtained in 1979 by Lovász, who proved that the chromatic number of the Knesset graph with parameters n and k is n minus 2k plus 2. The Knesset graph, denoted here by k of n and k, is the graph whose vertices are all the k subsets of the integers from 1 to n, where two such sets are adjacent in the graph if they are disjoint. Lovász used the Borsuk-Ulam theorem from algebraic topology to precisely determine the chromatic number of this graph. This result was extended and generalized in various ways, and one such extension was obtained by Scriver, who studied the subgraph of the Knesset graph k of n and k induced by the collection of all k subsets of the integers from 1 to n with no two consecutive integers modulo n. He proved, again by a topological argument, that this subgraph has the same chromatic number of n minus 2k plus 2, and this subgraph is commonly referred to as the Scriver graph. It is denoted here by S of n and k. The proof of Aharoni et al. For the existence of an independent set that fairly represents any given partition of the vertex set of a cycle uses the chromatic number of the Scriver graph, whereas the proof of Ishay and Munir is based on what is known as the octahedral Tucker lemma that can be viewed as a combinatorial formulation of the Borsuk-Ulam theorem that was applied by Matuszek in an alternative proof for the chromatic number of Knesset graphs. Since these proofs are based on tools from topology, it is perhaps not surprising that they only guarantee the existence of an independent set that fairly represents the partition, but they do not suggest an efficient algorithm for the search problem of finding such an independent set, given a cycle and the partition of its vertex set. The goal of the current work is to understand the computational complexity of such problems. So before presenting the results, let me briefly introduce some complexity classes of total search problems. The complexity class TF&P was defined by Megiddo and Papadimitriou in 1991 as the class of all the total search problems, those problems for which every input is guaranteed to have a solution, where the solutions can be verified in polynomial running time. In 1994, Papadimitriou initiated the study of total search problems in view of the mathematical argument that lies at the existence proof of their solutions. He defined several complexity classes, subclasses of TF and P, each of which corresponds to a certain mathematical argument. One such complexity class is PPA, polynomial parity argument. This class corresponds to the simple fact that in every undirected graph with maximum degree 2 that has a vertex of degree 1, there exists another vertex of degree 1. So PPA is defined as the class of all problems that can be efficiently reduced to a canonical problem called leaf, in which given a circuit that represents a graph with maximum degree 2 and given a vertex of degree 1, the goal is to find another such vertex. Another class defined in this way is PPAD, which is a subclass of PPA that can be viewed as the analog of PPA for directed graphs. PPAD is defined using a canonical problem known as end of line, and the class PPAD is known to perfectly capture the complexity of several important search problems of interest. Already in Papadimitriou's paper, it was shown that the search problem associated with Sperner's lemma is PPAD complete. And over the years, PPAD completeness was proved for several other problems, such as the one associated with the Nash equilibrium theorem. For PPA, however, until a few years ago, no natural PPA complete problems were known, whereby natural I mean that the problems don't involve circuits and Turing machines in their definition. The situation was changed following recent results of Philos, Ratsikas, and Goldberg, who proved the PPA completeness of a problem called consensus halving, and they used it to derive the PPA completeness of additional classical problems, like the problem of splitting necklaces with two sieves and cutting discrete sandwiches. In the current work, we contribute a few additional problems to the list of PPA complete natural problems, and now we are ready to present the results. We start by introducing the problem called fair independent setting cycle. In this problem, we are given as input a cycle G and the partition V1 up to Vm of its vertex set. And the goal is to find an independent set of G that fairly represents the partition. As mentioned earlier, the existence of a solution to every input is guaranteed by a result of Aharoni et al. And here we show that the problem is PPA complete. We next consider the first splitting cycle problem of finding two disjoint independent sets of a cycle that fairly represent a given partition and cover together all vertices but one from each part Vi. In fact, we consider here an approximate version of the problem with parameter epsilon, where the two disjoint independent sets, S1 and S2, are required to include at least half minus epsilon fraction of the vertices of each Vi. Here, the existence of a solution is guaranteed by the result of Ishay and Munir already for the exact version of the problem with epsilon equals 0. And this exact version is shown here to be PPA complete. We further show that the problem is unlikely to have a polynomial time algorithm even for a certain constant positive epsilon, because for such an epsilon, the problem is shown to be PPAD hard. We finally consider a problem that corresponds to colorings of Scriver graphs. In the Scriver problem, we are given as input a circuit that represents a coloring of the vertices of the Scriver graph S of n and k using n minus 2k plus 1 colors. Recall that this is smaller by 1 than the chromatic number of the graph, which is n minus 2k plus 2. So such a coloring must have two adjacent vertices with the same color. And our goal in this problem is to find the monochromatic edge. Using the connection discovered by Aharoni et al. Between fair independent sets in cycles and the chromatic number of Scriver graphs, we derive the PPA completeness of this problem as well. The proofs of the results are based on a chain of reductions. Our starting point is the consensus halving problem that was proved to be PPA hard by Philos, Vatsikas, and Goldberg. We show that this problem is efficiently reducible to the fair independent set in cycle problem, which is reduced to both the fair splitting cycle problem and the Scriver problem. These two problems can be reduced to a problem associated with the octahedral Tucker lemma, which is known to lie in PPA, essentially already from the original work of Papadimitriou. This is how we get the PPA completeness of the three problems. I would like to briefly describe now the high-level idea of the main reduction. So for simplicity of presentation, let's focus on a direct reduction from the consensus halving problem to the exact version of the first splitting cycle problem. The consensus halving problem with parameter epsilon is defined as follows. We are given m probability measures denoted by mu1 up to mu_m, defined on the interval from 0 to 1. It can be assumed that the probability measures are given by their piecewise constant density functions, and our goal is to partition the interval 0, 1 into two pieces, I plus and I minus, so that the measure of every mu I on the two pieces is approximately equal up to an additive error of epsilon. The crucial point here is that the partition of the interval into the two not necessarily connected pieces should be made using relatively few cuts, not more than m, the number of given probability measures. And it is known that such a solution exists even when epsilon is 0. For illustration, consider this density function that corresponds to mu1 and consider this density function that corresponds to mu2. As you can see, in this case, even one cut suffices to break the interval into two pieces with the same measure by mu1 and by mu2. The consensus halving problem was shown by Philos, Vatsikas, and Goldberg to be PPA hard even when epsilon is inverse polynomial in M. Our goal is to transform an instance of this problem into an instance of the first splitting cycle problem, a cycle and a partition of its vertex set, so that given two independent sets of the cycle that fairly represent the partition and include all vertices but one from each part Vi, one can efficiently obtain the cuts of the interval 0, 1 that provide the required pieces I plus and I minus. The reduction has two steps. We first apply a discretization argument that was previously applied by Philos, Vatsikas, and Goldberg to prove the PPA hardness of the necklace splitting problem. Here we associate with the density function of mu I a collection Vi of vertices. To do so, we consider the blocks that define this function. we partition every such block into blocks of some fixed small volume, and we define for each of them a vertex of Vi located in its middle. As you can see in the figure, in this example, we partition the block of mu1 into 4 parts of a fixed volume, and we put a red vertex of V1 in each of them. We then partition the blocks of mu2 into some parts with the same volume, and we put a blue vertex of V2 in each of them. The idea is that the number of vertices of Vi in every sub-interval of 0, 1 approximates the measure of mu I in this interval. After constructing the vertices of every probability measure, we put all of these vertices in a path. The vertices are ordered in the path according to their locations on the interval. So here are the red vertices of V1 and here are the blue ones of V2. The goal now is to partition the path using relatively few cuts into 2 pieces, each of which contains roughly half of the vertices of every set of the partition. In order to relate this problem to independent sets that fairly represent the partition, we need an additional simple trick done in the second step of the reduction. Between every 2 consecutive vertices of the path, we add a new dummy vertex, and we put all the new vertices in a new set denoted by V sub m plus 1. These are the white vertices in the figure. Finally, we simply close this path by another edge and get this cycle. For correctness, we need to argue the 2 disjoint independent sets in the obtained cycle, which fairly represent the partition and cover almost all of the vertices, can be used to obtain a solution to the original instance of consensus halving. The idea is that those few vertices that are uncovered by the 2 independent sets can be viewed as cuts, and every path between 2 such cuts alternates between the 2 given independent sets. By the white vertices of the construction, it means that only one of the 2 independent sets contains in such a path original vertices with colors different from white. Hence, every such path can be naturally assigned to one of the 2 pieces required by the consensus halving problem. In fact, because of the white vertices, we get from the reduction a partition into m plus 1 sets. So the partition of 0, 1 into I plus and I minus might involve n plus 1 cuts instead of m, but luckily the consensus halving problem is PPA hard, even if we're allowed to use m plus 1 cuts. I would like to end the talk with a couple of open questions. In this work, we consider the fair independent set in cycle problem, in which given a cycle and the partition of its vertex set, the goal is to find an independent set that fairly represents the partition. It is shown that this problem is PPA complete, and it would be interesting to understand the complexity of this problem restricted to instances in which the size of every part of the partition is bounded from above by some constant. More specifically, the special case of the problem where the vertex set is partitioned into sets of size 3 is closely related to the search problem associated with the cycle plus triangles problem, and it would be interesting to understand its complexity. Another result of this work is the PPA completeness of the Scriver problem, which given a succinct representation of a coloring of the Scriver graph with fewer colors than its chromatic number, asks to find a monochromatic edge in the graph. In this context, it will be nice to answer a related question asked by Dan, Kfen, and Kulkarni regarding the complexity of the analog problem for Knesser graphs. The Knesser graph contains the Scriver graph as a subgraph, and it has the same chromatic number, so it will be interesting to figure out if finding a monochromatic edge in a Knesser graph given a coloring that uses fewer colors than its chromatic number is PPA hard as well. Thank you for your attention.